thing that just started. Did you guys hear that I just started recording?
What?
Yeah? Okay. So we basically finished everything that I wanted to say about graphs of polytopes, and I want to tell you today about something, about a couple of things. So one thing I want to tell you is about polyhedral complexes. And then subdivisions and triangulations. Okay. And maybe let me tell you very quickly one of my main goals for the class today is to make concrete an idea that is pretty simple intuitively, but maybe it's not so obvious. If you have a polygon, then you know that that polygon can be cut into triangles very easily. And I've noticed several of you in your arguments have wanted to say that in higher dimensions, that you want to take a higher dimensional polytope, and you want to somehow argue that you can take that thing and cut it up into simplices. And that seems obvious, and it is true, but it requires a proof. And so that's basically what I want to do today, is prove that any polygon can be triangulated. And on the way there, we're gonna see some notation and some conventions. Okay. So first, let me define for you a polyhedral complex. So first, let me just tell you what it is, and then we'll run out the mathematics. A polyhedral complex is basically what you get when you take a bunch of polyhedra and you glue them together. Okay, so for example, maybe here I have a cube, and then I take that and I glue it to a square pyramid, and then maybe I glue a square onto this side, and then maybe I glue a hexagon over here, and then maybe I glue an edge like this, and so on. Okay. So that's an example of a polyhedral complex. Okay. So this is going to be a finite collection of polyhedra let's say in RD, such that first you have this kind of silly condition that the empty polytope should be part of your complex. Okay. Then if you have a polytope F in the complex, then any face of F is in the complex. Okay. So what I'm saying is, for example, that because this cube is part of my complex, then each one of its square faces is part of the complex, or each one of the edges is part of the complex. Okay? And so that means that when you see this picture, and you think of it as a polyhedral complex, the collection of polyhedra that I'm talking about is not only the collection of the kind of biggest polyhedra that you see, but also all of the smaller faces, all the vertices, all the edges, and so on. Question?
Does the second line say polyhedron?
A finite collection of polyhedra. Yeah.
Does that mean that the elements in the set individually are convex?
That's right. So each that's a good point. Each one of these things is what we've called a polyhedron. In other words, it in particular is convex. But then when you glue them together, you're going to get something that might not necessarily be convex. Okay. The third condition is that if you have two polytopes F and G, two polyhedra F and G in your complex, then their intersection is a face of both of them. Okay? And maybe the best way to understand this is with a non-example. Okay? So if you consider this triangle glued with that square, then that does not deserve to be called a polyhedral complex. And the reason is that when you intersect F and G, then you're going to get this piece over here, which is a face of G, but it's not a face of F. Okay? So we're not satisfying this property. Okay? So this is the kind of thing that I'm forbidding. Okay? So in other words, what I'm doing is I'm taking a bunch of polyhedra and gluing them face to face. Okay? So glue polyhedra face to face. That's what you want to think of. Okay? Does that make sense? Do you guys have any questions about that? Yeah. So, for example, this is fine. Is that what you're asking? So this is fine because the intersection of this hexagon and this triangle is a point which is a vertex of both. That's right. So that's a polyhedral complex. And the underlying set is denoted by like this, and it's just the union of all the polytopes, of all the polyhedra in there. Okay, so it's kind of the underlying space. So maybe it's better to call it the underlying space. Okay. So the underlying space is just the union of all the polytopes in there. This notation? So it might be a little bit confusing because the notation is the same as size, but we don't mean the size. So when I write like this, like absolute value of a polyhedral complex, that means the union of all the polytopes in the complex. It's not related to the size. I agree it's unfortunate notation because you might think that this is the number of polytopes in the complex. But that's the notation that we normally use. Okay. Let me say that this is an example of a polytopal complex because all my polyhedra are polytopes. They're all bounded. If that's the case, then I call it polytopal. And I should also mention that you might know from if you've taken topology about simplicial complexes. Okay? And a simplicial complex is a collection of simplices in RT. Okay. Now, one thing, if you have taken a little bit of topology, then there's one difference that I would like to point out, which is that here we are taking these things to be physical polytopes that live in RD. Okay? Whereas if you learn about this in topology, then you don't want to restrict this to living in a concrete realization in RD. And that means, for example, that in topology you can build a Mobius band. Think about whether you can do that in RD, in R3, for example. You avoid a lot of the complicated topology by saying that these are actual physical polyhedra. Anyway, I think that only means something to you if you know some topology. If you want to talk more about this, then I'm happy to talk to you. But you know, a simplicial complex then is just a tetrahedron, then glued to a triangle, then an edge, so on. Okay. That's an example of a simplicial complex. Okay. So now I want to talk about what it means to subdivide a polytope. A subdivision of a polytope P is basically going to be a polyhedral complex, in this case polytopal, right? Because this is a polytope. Complex C whose underlying space is P. Okay? But we also demand that the vertices of C equal the vertices of P. In other words, that you don't add any new vertices. So let me tell you what I mean by this. So for example, if I have a hexagon, then a subdivision is something like this. Okay? Where all of these triangles are filled in, and you see that all the triangles are glued face to face. That's an example. So that's an example of a subdivision of this hexagon. Let me try to draw a more interesting example. So in 3 dimensions, then what we need to do is cut this up. And so, for example, one thing that I could do is first cut off, make this cut, and isolate this tetrahedron. Okay, so then I get a tetrahedron, and I get kind of a square pyramid. Okay, and then I'm going to take that square pyramid and I'm going to subdivide it, for example, like this. Okay, and then it might be hard to see this to understand this picture, but if you stare at this long enough, you'll see that I've cut up this prism into 3 tetrahedra. Okay, so those are good examples of subdivisions. What's a non-example? What's the kind of thing that I don't allow? A non-example is, for example, taking a hexagon and dividing it like this. And the issue here is that even though this is a polyhedral complex, because all these simplices are meeting face to face, the problem is that I've introduced a new vertex, and I don't want to allow that. Okay? So this is the kind of thing you're not allowed to do. Okay? So that's a subdivision. And again, let me change the definition a little bit. So I'm going to call this a triangulation if all the pieces are simplices. Okay? So for example, both of these are actually triangulations. Okay, any questions about that? It all makes sense? It's good? Okay. So again, I think in the plane is kind of clear that if you take any convex polygon, then you can just draw diagonals to triangulate this thing. How am I going to do this in higher dimensions? So let me not say claim, let me say proposition, because we're going to prove it. Proposition, any polytope P has a triangulation. Now, there's different ways of proving this, okay? Let me give you one sketch of a kind of proof that you can do, which is not the proof that I'm going to do. So here's sketch of proof 1. Basically, you're going, and actually, I think some of you already wrote down a proof like this for homework 1. Okay? The point is this: that if you have a polytope, then if your polytope is a simplex, then you have nothing to do, right? If it's a simplex, then it's its own triangulation, and there's nothing to do. If it's not a simplex, then what you can do is find hyperplanes that pierce through the polytope. And you have to be careful, as Nick pointed out yesterday. You have to be, or last time, you want a hyperplane that basically is spanned by vertices of the polytope and separates the polytope into two. If you can do that, if you take the polytope and you take a hyperplane and cut it in two, then you can make an induction argument that says triangulate this part, and you'll be done. By inducting, for example, on the number of vertices of the polytope. So this is an argument that you can make and make precise. But I want to do a kind of a more fun argument and a useful argument, because what I'm going to do is I'm actually going to construct triangulations. So if you really want to do this, then how can you do it? And okay. And I need you to pay attention now, because this is going to become a dynamic movie and not something that you can stare at the board, okay? Because this is really. So I need you to look up while I'm doing this. So let's say that. So let me first sketch the idea, and then I'll make precise what I mean. Let's say that you take that you have a polytope that you want to triangulate, okay? So what I'm going to do is the following thing. I'm going to go to one dimension higher. Okay, so maybe this is in the plane. And so now I'm going to move to three-dimensional space, okay? And I'm going to take my polytope. This is hard to draw, but I'm going to do my best. So my polytope now is living on a plane inside R3. Okay, these are two of the three dimensions, but I have a third dimension. Now, what I'm going to do is that I'm going to take each vertex and now lift it to some height. And when I say lift, I mean in the other coordinate direction. And this is where it's going to get very hard, but let's see. So maybe I lift this point over here, then I lift this point over here, I lift this point over here. Okay? That's what I'm going to do. Take each one of these points and send it up. And then I'm going to look at the polytope that is spanned by those vertices. Okay? Let me try to draw that one for you. So you see why this is so hard, because I need things not to line up so that this picture makes sense. So let's move this guy up a little bit more. So I think polytope is going to look like this. No? I'm not done, but but I might make a mistake, so please check me. I'm very happy that you're saying no. I still have to join the back vertex, which is joined to this. It's joined to this, and then this is joined like this and like this. You disagree? Why don't we give names to these things so that you can... so let's say that this is 1, 2, 3, 4, 5. And now this is going to be 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. So I'll receive any objections now.
Why doesn't 2 prime have maybe edge with 4?
It does. You're right. I'm missing an edge from 2 prime to 4 prime. Agreed? I better be missing something because this is a 3-dimensional polytope and this guy has only 2 edges. I think that's it. Okay. What am I doing? This is kind of strange, right? But the thing is that now what I want you to imagine is, imagine that you're standing inside this polytope and you're looking up. So what you're going to see is you're going to see kind of the polytope itself, but now it has folds coming from the fact that this is a 3-dimensional thing. Okay? So in other words, if you stand below the polytope and you look up, what faces are you going to see and what faces are you not going to see? Can you tell me? So from below, I can see the face 1, 2, 3, right? So let me shade that one in. This is dangerous to shade it in, but maybe if I'm careful, it'll be okay. What else can I see? I can see 1, 3, 5. What else can I see? Does it depend on the perspective?
No.
Imagine that you're standing really, really, really far down. Okay. Then it doesn't depend. And actually, you're going to see 3, 4, 5. Those are the faces that you see. In other words, if you look at the normal vectors pointing out of the polytope, these are the 3 that point down, and the other ones point up. Okay. So what I claim is that now you can translate that and just say, okay, so 1, 2, 3 is there, then 1, 2, 3 is here. 1, 3, 5 is there. So 1, 3, 5 is here. And 3, 4, 5 is there, so 3, 4, 5 is here. Okay. And I claim that that always works. It's kind of a fun way to construct triangulations.
So you have to, if you had another vertex of P, would you have to go to R4?
No. So you only have to go up 1 dimension. So if you are a d-dimensional polytope, then what you're going to do is look at the d-dimensional space living inside d plus 1 dimensional space. Okay, so here you have d dimensions, and you only have one more dimension, and that's the dimension that you're going to use to send each one of these vertices up. Okay. Yeah, I'll take any other questions. It's very important that you understand this, and by the way, so we need to also balance this picture, which is a geometric picture, with a kind of an algebraic proof that we're going to do.
So can we figure out just from the numbers for those height values what needs to be connected, or is there more qualitative?
It's a very good point. Given those heights, I mean, I told you this is constructive. So, is it really constructive? How do you know, given those heights, what are the faces that you're going to see? I mean, I'm kind of giving it to you in a kind of a shady way, saying, okay, look up and see what you see. But if this is a 5-dimensional polytope, you're not going to have very good luck looking up to see what you see, right? So I'm going to make more precise what I mean by that. But the answer is that yes. I mean, actually, I'm going to tell you right away. What I'm going to say is, look at the facets of this polytope and look at their normal directions pointing out of the polytope. Okay? And look at the last coordinate of the normal direction. So if you look at these three, they're all pointing down in the last coordinate. If you only care about the z coordinate, then these three purple faces, the normals point down, and the other faces point up. Okay? And so I'm saying take the ones that point down, and I claim those form a subdivision. Okay? And of course, by analogy, the ones that point up also have to give a subdivision. Okay? But so that means that you can actually do this in practice if you know how to compute facets of a polytope, right? I mean, if I give you the coordinates of this guy, and if I give you the heights, then you have a polytope here, and as soon as you write down the inequality description for this guy, the inequality description tells you what the normals are, and then you're going to be able to do this in practice.
Okay. Wouldn't you have to know, I mean, in your thing there, I would assume that 2 is higher than 5, so you'd have to know that 5 is connecting to 4 and not to 2.
So I was trying to draw the picture so that 1, 2, and 5 were at the same height.
1, 2, and 5
But-
are all the same height?
Yeah. But anyway, maybe what I'll do is let me actually write down formally what I'm trying to draw here, and then maybe that will answer some of your questions. Let me say that a subdivision constructed in this way is called a regular subdivision, and this in this case is a triangulation, so I call it a regular triangulation. Okay. Did you have a question, Mela? You know, also, I'm going to recommend it, and I'm going to recommend this very seriously. Do an example. Take a polytope, you know, draw it. Take a polygon, because I mean, you're only going to be able to do it for polygons. Take a polygon, lift it, and really just carry this out, because it all depends on what you're seeing in this picture, and sometimes these pictures are a little bit hard to understand if you didn't draw them yourself.
I guess what's your rule for connectivity is what if you're not on the same level, then you connect. If you're on the same level, you only connect if you were before.
So the rule for connectivity in the new polytope is just, are you or are you not an edge of that polytope? Yeah?
But in order to do this, you have to raise all of the points to the same heights. No. Because if you had, like, let's say, like 1, 2, 5, and 3 were all on the same height, then you would just have the 1. You wouldn't connect 1 and 3, and then so you wouldn't actually have a triangulation.
So that's a very good point. So maybe, so what you're saying is that I might get a subdivision or a triangulation depending on how smart I am about this. For example, if I lift all the vertices to the same height, then not a lot is going to happen. and the subdivision is going to be just the polytope itself. So I want to be a little bit smarter, and I mean, depending on what I'm trying to do. If I want a triangulation, then I should put things at different heights so that they don't line up. But it's not only at different heights. You see, actually, I had to change my drawing because things had lined up like I didn't want to. Okay? But the point is that if you choose the heights generically, if you just choose random heights, then things aren't going to line up and you're going to get a subdivision. But let me make that more precise. In short, the answer is you're right. I have to be more careful. So regular subdivisions, what does this mean? I'm taking my polytope P and I write it as the convex hull of the sets of the vertices V. Okay? And I'm going to choose a height function for the vertices, so each vertex gets a height. Okay? And then I'm going to define a new polytope, which is the convex hull of the vertices of the form. So I take each vertex of my original polytope, and then I put as a last coordinate this height that I introduced. So this is going to live in one dimension higher. Okay? So you see here, this is P, and this is P prime. Okay? And then I'm going to say that a face f of P prime is lower if it is the maximal face in direction C for some direction C. Remember that we want our directions to live in the dual space. Some direction C whose last coordinate is negative. Okay? And it's going to be upper otherwise. Okay? So basically, I'm considering all the faces of my polytope P prime that I can point to, but making sure that in the z-coordinate I'm pointing down. I don't care about the other directions, but in the z-coordinate I have to be pointing down. All the faces that I can describe in that way are lower faces. Okay? Now let's consider the projection pi from P prime to P that just forgets the last coordinate. Right? So it takes x1 up to xd plus 1 and sends it to x1 up to xd. Okay? And then what I have is a proposition that if I look at the projections of the lower faces, then they're going to form a subdivision. And so this is for any height. And if my height is generic, it is general enough, then it is a triangulation. Okay. So now it's not relying on looking up. It's really putting this in terms that we understand what they mean mathematically. Yeah. So does the statement make sense to you guys? Is it good? Actually, let me change my mind about upper, because one thing you might realize is that there are faces that you might want to call lower and upper, namely faces that are kind of around the rim of the polytope. Okay? And I only care about the lower one, so let me just define this to be lower. Okay? Yeah.
When you say that H is general, would that, so if H gave you something in general position, would that work too?
Yeah. You know, I mentioned this already. Maybe I'll just say it again. The word generic. The word generic means whatever you want it to mean, so that the theorem is true. And you see this all over mathematics. If something is generic, then something happens. And really what this means is that for all H except those in a set of measure 0, this is a triangulation. Okay? But depending on the specific context, you might need to make a different definition of generic. And I think it's kind of a headache to say exactly what I mean. During the proof, during the course of the proof, you'll see exactly what I mean by this. Okay. Actually, let me just say it right away. Let's just do it for the generic case, and then the non-generic case is basically the same thing. Say H is generic if the vertices of P prime, they're all as affinely independent as can be. Okay, so I don't want to have 4 lie on a plane. I don't want to have 5 lie on a 3-dimensional thing. So, in other words, if any d plus 1 vertices of, any d plus 2 vertices of P prime are affinely independent. Okay. So what I'm saying here is that any 4 of these lifted vertices are affinely independent. Okay. They don't lie on a. They form a 3-dimensional thing. Now, how do I know that this happens almost always? Well, intuitively, I think it makes sense. You have very bad luck if you lifted things in a way that these points lined up. Okay. How do we make that concrete? Well, you could say that having things line up can be described by an equation, a linear equation that says that there's an affine dependence. Okay. And clearly, the set of points that satisfy an affine equation has measure 0 because it's of a lower dimension. Okay. So let's just restrict to that very general case. So in this case, basically, what we'll have is that P prime is a simplicial polytope. Remember, simplicial means that all the faces are simplices. And that must be true because if you had a phase that was not a simplex, then those things would have to be dependent, right? If you had a quadrilateral as a phase, then those 4 points would violate this condition. Okay. And so in particular, all of these things are simplices. Okay. All of these things really are simplices. So let's go ahead and prove the different properties I'm going to save room for an observation here. So if you're taking notes, maybe save room here. So first, I need to prove that this is really a polyhedral complex. Okay. So that means that I have to check three things. The empty set is supposed to be in the complex. Okay. Well, this is one of those things that's kind of silly, and actually, if you see the way that I did this, strictly speaking, the empty set is not here. So I guess really I should take this with the empty set. That's always a condition that is not too interesting, but we need to make sure it's satisfied. Okay. Second condition. Suppose that you have a polytope F in the complex, and you have G, which is a face of F. So we want to prove that G is also in the complex. Okay, but how does this look in this picture? Here we have some face in the complex. By the way, let me make sure that this is clear. That what I'm doing here, what I'm stating here is the following. I'm saying take P, lift it, look at the lower faces, and project them down. And I haven't drawn that in here. But really what I'm saying is that if you look at the face 1 prime, 2 prime, 3 prime, then the projection is going to be the triangle 1, 2, 3. If I project 1 prime, 5 prime, 3 prime, then that's going to be this triangle. And if I project 3 prime, 4 prime, 5 prime, then I'm going to get this triangle. And so the claim is that this set of things is a subdivision of P. Okay? So let's go back to what I was saying then. I'm taking a face in the complex. Okay, so that means that here I have a face, but by definition, that means that this comes from a face up here. Right? Maybe we call it F prime. Okay. Now, the observation that I want to make is that actually, if you look at this projection, first of all, it's an affine map because projections are always affine maps. But the thing that I want to point out is that this is an affine isomorphism on each face. Because if you restrict to each face, then this is a one-to-one correspondence. Okay. How could it not be a one-to-one correspondence? If you had things that were projected and lost dimension. Okay. For example, if you had like a hexagon in the z direction, which when you projected it, it turned into a line. Okay. But that cannot happen because of this condition of genericity. Okay. So that's the observation that I wanted to make here. That pi is an affine isomorphism from each lower face F prime to its projection. Okay. In other words, what I'm saying is that when you project each face, you're not really losing anything. So then F comes from F prime. Now G is some face of F. But then because these two guys are affinely isomorphic, that means that you clearly have a pre-image here, G prime, which is a face of F prime. Here I have a typo, right? I meant to say F is the projection of F prime, and G is the projection of G prime. Okay? So how do I know that G is in the complex? Well, I need to check that G prime is a lower face, right? Because those are the only guys that land in the complex, the projections of lower faces. So why is G a lower face? Let me just say it in words. We know that F prime is a lower face, right? Which means that we point to it in a direction with z coordinate negative. That's the direction pointing to F prime. Now, how do we point to G prime? Remember that you just do an epsilon perturbation of that. So if this is C, then to point to G prime, you do an epsilon perturbation like this. And the point is that if the last coordinate of C was negative, then you're not going to make it positive with an epsilon perturbation, because you can make epsilon to be as small as you want. Okay? So F prime is lower, implies that G prime is lower, and therefore that G is really in the complex. It's really a projection of a lower face. Okay? So the second condition of being a subdivision holds. Third condition is that you have two faces. You have two faces, F and G. Let's say they're here, F and G. Okay? Well, they're projections of some faces here, F prime and G prime. Okay? Now, I want to say that F and G intersect face to face. That's what I need. In other words, that the intersection of F and G is a face of both F and G. But clearly, the intersection of F and G is the projection of the intersection of F prime intersect G prime. And the point is that here it is true that things intersect face to face. Why? Because these are faces of a polytope, and faces of a polytope intersect face to face. Okay? So because of this affine isomorphism condition, if this segment is a face of F prime, then when you project, it's also going to be a face of F. So this is basically inherited from the projection. Okay? So that means that this really is a polyhedral subdivision. But the last thing that I need to prove is that this really is a polyhedral subdivision of the whole polytope. Right? Because now we know that these things land inside P and they glue correctly, but do I cover the whole polytope? That's the question. So I need to show that I cover the whole polytope, and the way that I do this is the following. I say, take a point in the polytope. Okay? Now, here I have my thing of one higher dimension. And then what I'm going to do is look at where this P could come from, okay? So I'm going to look at this whole line, the vertical line that goes through P. And you see that it intersects. It intersects the polytope like this, and then it leaves again. So I'm taking P and P, and I'm saying consider this is pi, right? So look at the inverse of the projection. So it's basically going to be given by this segment from P0 to P1. Okay? So what I'm going to claim is the following. Let's call this face F. Okay? Let P0 be inside face F. Okay? So what I want to claim is that this face F has to be a lower face. And if it is true that it's a lower face, if I prove that this is a lower face, then it is one of the purple things that I get to project down, and that means that I get to cover P. So once I prove that P0 is in a lower face, then the projection is going to send it to P. And let me just quickly make the argument for why it's true that F is a lower face. Say that F is the maximum phase in direction C. Okay? So maybe C points like this. That means that the value of C at P0 has to be bigger than the value of C at P1. Right? Because P0 is in the maximal phase and P1 is not in the maximal phase. So that means that C dot P0 minus P1 is positive. But now if you look at the vector P0 minus P1, you'll notice that that is a vector in the vertical direction. In other words, its coordinates are 0, 0, 0, 0, 0, minus something.